In this video, we're going to explore the hydrohalogenation of alkynes. Keep in mind an alkyne has two pi bonds. Each pi bond reacts similarly to the reaction in Chapter 6. We are also going to study the halogenation of alkynes. We'll choose a mixed halogen so we can explore the regioselectivity, Markovnikov, and once again, two pi bonds. React 1, you get this result, anti-stereoselectivity and Markovnikov regioselectivity, and Markovnikov regioselectivity for the final product. And we'll finish off by exploring what happens if you use internal alkynes instead of terminal alkynes. Terminal alkynes are characterized by ending the chain, and you'll see an internal alkyne where it's in the middle of the chain later. With the mechanism, pi electrons have to attack the most positive atom, so we'll get started here. Pi electrons attracted to the positive hydrogen. Pi electrons down here attracted to the more positive bromine. Sigma bond between H and the halogen breaks, makes a chloride. Sigma bond between the Br and the Cl breaks and makes a chloride. The main difference is down here, bromine has a lone pair that hydrogen doesn't here, so we'll show that with an extra arrow here to make a triangular intermediate. Which carbon does the bromine come back to? It comes back to the more substituted carbon, because that's the one that would be a better carbocation, and the result of the top mechanism will be a carbocation on the more substituted carbon, because that'll have more hyperconjugation. The result on the bottom mechanism will be a cyclic bromonium intermediate. We'll show both right now. Cation on the carbon that has more bonds to carbon will be attacked by chloride to make the product indicated above. Lone pair goes all the way to the carbon of the cation, makes a sigma bond. On the bottom, the chlorine is going to do a backside attack on the triangle. Every triangle we've made, we do a backside attack on the more substituted carbon in the next step after you make the triangle, without exception, and backside attack, and you break the bond on the more substituted carbon to the bromine, thus neutralizing the bromine, giving these results here. The Markovnikov, where the more electronegative chlorines on the more substituted carbon, and I know you don't see a new H here, but there's two H's there. There was only one before. In the very first step, we got our second H. In this one down here, cyclic bromonium is attacked on the more substituted carbon, backside attack, gives an anti-stereoselectivity with chlorine on one side and bromine on the other. I believe this mechanism here would have given this result shown here, this result here with the chlorine on the bottom. But in effect, that is really the same as this result here. So there was no need to draw it like this. Second part of each mechanism, same as the first part. We attack the hydrogen. Sigma bond between H and Cl becomes a lone pair on chlorine, making it into chloride. Similarly down here, we attack the more positive bromine. Chloride leaves, and the bromine lone pair comes back to the more substituted carbon. I had to put the lone pair on there. Here it is coming back to the more substituted carbon as promised, giving these two results here. Carbocations formed here. Gets attacked in a very fast step by the lone pair on chloride, giving us the product indicated above. And And underneath here, backside attack on, you guessed it, the more substituted carbon that spends more time with a positive charge, breaking the bond, neutralizing the bromine here, giving these results. We have the double Markovnikov geminal dichloride. And I'm pretty sure geminal is a new word for some of us. Geminal means both chlorines are on the same carbon. Sort of like the zodiac sign Gemini for twins. And the result here, backside attack on the more substituted carbon. The two chlorines are geminal. The two bromines are geminal. The pair of chlorines is vicinal to the pair of bromines. Vicinal meaning adjacent carbons, as we've seen before. And I noticed there's a mistake in our mechanism down here. So you can't have 5 bonds to carbon. This mechanism would have created a 5th bond to carbon right here. Let's fix that. There we go. Compensate for the new bond by breaking the old bond. Backside attack, we call that. One further comment before we move on to a brief discussion of internal alkynes versus our terminal alkynes that we saw here. This cation is much more stable than this cation for reasons beyond hyperconjugation. This cation here has a chlorine with lone pair, which can resonate with the carbocation, thus completing the carbocation's octet, giving this resonance form here. As you can see, no octet violations here. So it's not all about hyperconjugation. This cation is the major cation because of resonance. All right, let's explore what would happen to an internal alkyne under these reaction conditions. You would initially get a 50-50 mixture of 3-chloro-3-heptene and 4-chloro-3-heptene. And the next mole of HCl would create these two products. This would be 3,3-dichloroheptane, and this would be 4,4-dichloroheptane. And why do the chlorines go on the same carbon as the original chlorine? Has nothing to do with hyperconjugation, I'll tell you that. It has everything to do with the fact that the better cation is the one that has the halogen on it, for this reason over here. So we get a 50-50 mix of two products. That's the case. Similar story for the halogenation of alkynes. We would get E, 3-bromo, 4-chloro, 3-heptene, and E, 4-bromo, 3-chloro, 3-heptene, 50-50 mixture of the two. Because this cyclic bromonium has no preference for the chloride coming from here or from here. They have the same substitution, therefore the same steric hindrance and the same hyperconjugation. Second mole will create these results. This molecule will create a 50-50 mix of this and this. Once again, there's no preference of which carbon gets attacked by the chloride. So half the time the second chlorine comes from the right side and half the time from the left side. Similar story over here. You're going to make a cyclic bromonium from here. Half the time the new chlorine comes from the left, half the time from the right. And these two products here are identical. Fact is, you made a big mess. You got 3 products. You'd get small amounts of these two and a larger amount of these two. Not a very useful reaction when you get that many products. I hope you found this video about hydrohalogenation of alkynes and halogenation of alkynes to be useful, and I look forward to our next video. Until then, goodbye.